before the Christmas break, before Savannah, we did Einstein. We did a unit on kinematics. D equals VIT plus a half AT squared. VF equals VI plus AT. VF squared equals VI squared plus 2AD. And the other one that I always forget. Kinematics is the study of how things move. This unit is going to be the study of why things move. See the difference? Why do things move? Because of forces. The fancy word is dynamics, but forces. So that's why it says in the headings, Unit 5, forces. And it all starts with Sir Isaac Newton. Well, okay, Galileo was starting to tumble onto some of the stuff shortly before Newton, but Isaac Newton really revolutionized physics. First of all, we need to define what a force is. I'm going to give you both a good and bad definition. It's a good definition because it's pretty easy. A physicist would call this a terrible definition. I'm going to tell you that a force is a push or a pull. Adam, if you were a quantum theorist, you would say it's actually an interaction when objects exchange leptons? Leptons. You know what? It's a push or a pull. So much like everything I'm teaching you, Kenzie, if you start going down to the quantum level, I'm teaching you everything wrong. If I start going up to the general relativity level, I'm teaching you everything wrong. But for the most part, this will be, Riley, a pretty good model. In fact, I'm going to teach you a whole bunch of different forces. A physicist would say, actually, there's only 4 forces in the universe. There's the strong force, there's the weak force, there's electromagnetism, and there's gravity. And then a relativist would say, actually, gravity isn't a force, it's a curvature of space-time. There's only 3 forces in the universe. Logan, we're not going to be that fussy. Is force a vector or a scalar? This time in this unit, direction is going to start to make a big difference. Force is a vector. It matters which way you push on something. It matters which way you push on something. What would be a good letter to use for force? Capital F. Although since it's a vector, I should put the vector symbol above it. Units. Force is measured in newtons. Capital N. Named after Sir Isaac Newton. In the imperial system, force is measured in pounds. Pounds are a measure of force, not of mass. We're going to often talk about the net force. What we mean by the net force is the vector sum of all of the forces. That sounds tricky, Riley. It's not. Can you tell me, let's do this. Let's put a little compass rose right here. North, east, south, west. And what we're going to do is we're going to figure the net force, both magnitude and direction. 5 newtons that way and 2 newtons that way. What's that the same as? What's the net force? Don't overcomplicate it, Antonio. Direction. Direction. Please tell me when I said we're going to draw a compass rose that you drew the compass rose, and so now we have our directional frame. Direction. Okay, so we could say 7. Now, there's a bit of a problem because the letter N stands for newtons, but when we're talking about direction, what does the letter N stand for? It's going to be confusing. So to show that it's a direction, we put an @ symbol, east. A little trickier now, Riley. What do you think the net force in B would be? Direction. Which direction is winning? Yes. Do you see it? He thought about it and then it became obvious. Oh, east. Yes. And that's the larger force, the larger unbalanced force will be the winning direction. So you said 3 units newtons at east. Ben, what do you think C is? It's a trick question. What do you think the net force is? Yes. This is a and no direction because there's no force technically. This is a very, very important situation. Later on, you'll learn that if you know that the net force is 0, you know this object can't be accelerating, which means it's either at rest or it's moving in a straight line at a steady speed. Hugely useful. And in fact, you'll learn later on today that if you know there is an unbalanced force, object A must be accelerating east. Physics 12 will go two-dimensional. We'll start saying, okay, what if everything isn't in a nice straight line? And I'll teach you something called vector mathematics. If you want to know the answer, it would look like this. 6, 3, and we would use trig and Pythagoras to find the magnitude and the direction. You add vectors tip to tail. I'm hoping to get to a mini vector unit at the end of this year. I didn't get to it last year, so I'm hoping to speed up a tiny bit. Newton's laws of motion. Put your pencils down. I got to pause the video for a second. So along comes Uncle Isaac Newton, and he says, if all forces are balanced, the fancy phrase, the net force is 0, like the important situation that Ben pointed out earlier. An object has two options. It will either remain at rest if it was at rest, or it'll move in a straight line at a constant speed. I can summarize all that by saying, if the net force is 0, A is 0. Because if you're not accelerating, if you are already moving, you're going to keep moving at a straight line at a steady speed. If you weren't moving, you're not moving. So if the net force is 0, what's the acceleration? 0. But this is a very powerful statement because it also works backwards. If you're not accelerating, if A is 0, the net force must be 0. If you are accelerating, the forces can't be balanced. It's impossible. And I can even tell you in what direction they aren't balanced. It's whichever direction you're accelerating. That's where the unbalanced force is pointed. That's where you would have that, 3 east moment. Okay? So if an object is accelerating, changing its speed or direction, then the net force can't be 0. I'd like you to imagine that you're a passenger in a car and the driver makes a quick left turn. What do you feel during the turn? Probably you feel like you're getting pushed to the right. That's not what's happening. Newton's first law says this, Jackson, your body wants to keep going in a straight line at a steady speed. And the only way that we can cause your speed to change is by applying a force on you. The door is actually pushing against you. You're not pushing against the door. The door is pushing against you, and that's what causes you to move around. Now, it's a combination of the door pushing against you and friction between your seat and the pants that you're wearing as well. And also you have to exert a force on your head through your spine. But it's because you want to keep going in a straight line at a steady speed. So I wrote here, contrary to what your common sense might tell you, you're not being pushed to the right at all. The driver steers the car to the left. Your body wants to keep going in a straight line at a steady speed. Newton's first says that objects want... By the way, Newton phrased it, objects in motion tend to remain in motion, objects at rest tend to remain at rest, which is really confusing. Your objects with mass want to keep going in a straight line at a steady speed. You feel like you're getting pushed against the door by the force aimed towards the door, but your body is trying to continue straight ahead, and so you run into the door and the door pushes you. It's a very different idea than what you think when I'm getting pushed outwards. You're not. You're getting pushed inwards. Completely the opposite. I think I told you our bodies can detect acceleration, but it's always backwards. This is why. What your body is actually feeling is its own inertia. As a general rule, next page, any object tends to continue moving with whatever speed and direction it presently has. This can include zero speed, of course. So at rest is speed. When your driver accelerates the car, your body wants to stay where it is. This is why when you accelerate forwards, you feel like you're getting pushed backwards. You're not. You're at rest and your body wants to stay at rest. The back of the car runs into you. This is why I've told you that your body can detect acceleration, but it's always backwards. What you were really feeling was your own inertia being pushed forward by the car. And when you hit the brakes, your body wants to keep going in a straight line at a steady speed. The seatbelt has to apply a force on you to bring yourself to a stop. You are accelerating backwards, but because you ran into the seatbelt, you feel like you're getting pushed forwards. No, you're getting pushed backwards. Your body wanted to keep going in a straight line at a steady speed. This tendency that all objects with mass resist changes in their motion states is given a special name. Here's our word of the day, Logan. Inertia. Every object in the universe that has mass has inertia. And the more mass you have, the more you'll resist a change in your motion state. Pause the video first. Mine likes to say that you can think of inertia as the measure of the stubbornness of an object or its resistance to change. The bowling ball did not want to change direction. It was stubborn. It wanted to keep going in a straight line at a steady speed. Now, I'm pretending that these objects can think. They can't think, but we're trying to get an analogy. And so we're saying objects with more inertia are more stubborn. They resist change. They want to keep going in a straight line at a steady speed. Or if they were at rest, they want to stay at rest. What object has more inertia, a bicycle or a logging truck? Quick. Because of that, we can, just with that, Rowan, we can explain that a logging truck is more difficult to get moving, more difficult to stop, and more difficult to turn around a corner because you can also accelerate by changing your direction. Vectors have both magnitude and direction. How do we measure inertia? I'm going to treat inertia as the same thing as mass. This is not quite true. Pause. I'm going to be a bit fussy, Kenzie. I'm going to treat inertia and mass as the same thing. They aren't technically. When I told you that when you speed up, Einstein says mass increases, what he really was saying was inertia is increasing because you have a bigger and bigger resistance to acceleration. Okay? So this is only true for speeds lower than much less than the speed of light, but we're going to be staying there. Inertia or mass resists a force. That means objects with mass want to keep going in a straight line at a steady speed. I'm going to say that again, and you're going to fill in the blanks. Objects with mass want to keep going in a straight, at a steady, okay? Or if they're at rest, they want to stay at. You can think of mass as a measure of the stubbornness of an object. The more mass an object has, the less willing it is to change its motion state. So Newton's first law says if an object is at rest, forces are balanced. If forces aren't balanced, the object isn't at rest. And the explanation for why objects are difficult to accelerate is they have inertia, mass. Next page. So here's the short version of Newton's first law. If an object is accelerating, there must be an unbalanced force. Or if there's an unbalanced force, the object must be accelerating. Now, this is important to remember because acceleration is a vector. That means the acceleration can be changing speed or changing... Oh, huh? Yes. I saw that one on TV. I can do that. Maybe not with 10 guys. He's in better shape than me, but I can easily do 5. I could, you know what? I probably could do 10 because I'll bet you there's a decreasing return as more and more of you kind of interfere with each other. Because okay. And I was, oh, by the way, that's why I asked Jackson his height. I wanted a tall person in front because that makes it easier for me to deflect the force up. I didn't want Sam in front, sorry, because that would have made it more challenging. Okay. That partly explains why. Who's my football players here? Has your coach ever told you low man wins? There's the physics of it. Okay. How does Newton's first law help explain how seatbelts save lives? Because your body would want to keep going in a straight line on a steady speed. Yeah, absolutely. So, person would want to keep going forwards. You have to have an unbalanced force to bring you to a stop. What do you yell out when you want the front seat? Shotgun. You all know this. Why? Well, it comes from two areas. It's partly from the old stagecoach days. The shotgun seat was next to the stagecoach driver. You were the person with the shotgun protecting the payroll from outlaws and thieves. But in the 40s and 50s and 60s, when I was growing up, seatbelts weren't mandatory until I think I was 7 years old. Up until then, they were optional. And in the U.S., they weren't mandatory for quite some time. We used to make a joke. We used to say, shotgun, I'll be the first one out to inspect the damage. And what we meant by that was if you were in the shotgun seat, you're going to get launched as though you were getting launched out of a shotgun. You're going to be going through the windshield, and you would inspect the damage on your way past, was our kind of morbid little joke. So it kind of has a couple of different, shotgun is from the old stagecoach days, but that was the terrible joke we made out of that. If you've ever wondered why you yell why would you yell that? There's the history of it. Okay? So this is why the front seat is nicknamed the shotgun seat. Used to be because of stagecoaches. And in the 50s and 60s, our standard joke was, you're in the shotgun seat because you'll be the person catapulted through the windshield. Why wouldn't the driver get catapulted through the windshield? Steering wheel, but they're still going to die, but they won't be going through the windshield at least. Right? Why wouldn't you want a seatbelt on a motorcycle? Okay. Yeah, also because of Newton's first, we don't, you know what, I'll capitalize don't, want to be at the same speed as the wreckage. Right? So you want to separate yourself from, otherwise you could tumble with the wreckage and have it be landing on top of you. So we've thought of that too. Okay. Remember me rolling the tennis ball on the floor? Did it slow down and come to a stop? I'm going to ask you the same question. I want the same answer. I'm just going to phrase it differently. Did it accelerate? Yes. That means there must have been an unbalanced force acting on it. That's what Newton said. None of this Aristotle life force energy sucking into the earth garbage. No. And the other reason we have so much respect for Isaac Newton was he was doing this in 1580. This is how outer space works. At a time when we hadn't even invented hot air balloons, Isaac Newton was imagining in outer space, once you're away from any planets, if you fire your rockets, you can then shut them off and coast the rest of the way. You'll keep going in a straight line at a steady, because there's no forces acting on you, no gravity out there. So we got a lot of respect for him. He was doing some deep thinking. Manuel weighs 1,000 newtons and stands on the middle of a board that weighs 200 newtons. The end of the board rests on bathroom scales that are pushing upwards. It says fill in the correct weight reading on each scale. You don't realize how powerful Newton's first law is. It's a very, very powerful tool. So are you ready? Look at this first picture right here. Is he sinking into the ground like quicksand? Say no. Is he flying into the air like Superman? Say no. That means forces are, I'm looking for a word that begins with letter B, balanced. Has to be. That's what Newton's first says. What's the total force downwards? Add it up in your head, please. What's the total force downwards? What must the total force upwards be? Has to be 1,200. Is he standing dead center? So what's each scale pushing up with? 600 apiece, baby. Newton's first law is a very powerful tool, especially if you know something isn't accelerating. Because if it's not accelerating, then you know all the forces are balanced. Now Manuel has walked to the left a little bit. Is he sinking into the ground like quicksand? Is he flying into it like Superman? So the forces must be, I'm looking for a word that begins with letter B, Balanced. What's the total force down, Courtney? Add it up in your head. What must the total force up be then? It has to be 1,200. How many newtons do we have pushing up here? So how many must we have here? 350? Yes? Did I do the math right in my head? Engineers use this in bridge design all the time. So supposing you are designing a bridge and you know that the bridge has a weight of 20 tons and you're going to put a 12-ton truck on it. And you've done measurements, you know that this support is pushing up with 13 tons. How many tons must this support be pushing up with? Is the bridge sinking into the ground like quicksand? Is it flying into the air like Superman? No, you say? Then the forces must be, I'm looking forward to being letter B. So the total force down is 32 tons. What must the total force up be? 32 tons. So how much must this bridge support be pushing up with? 19? I think 19, yes? How does a car headrest, in terms of Newton's first law, the law of inertia, how does a car headrest help guard against whiplash when you're rear-ended? And this is very similar to the car accident story that I told you. I think I was recording on YouTube. Sorry, people on YouTube. But I told you that my coin container went shooting backwards. That's not what happened. It stayed at rest. My car got thrown forwards. Why did the coin container stay at rest? It had lots of mass. Does your head have mass? So it wants to remain at rest when you get rear-ended. So you'll feel like your head got shot backwards, but actually it stayed where it was. Your body got thrown forwards. How can we prevent this snapping of your neck? That's what the headrest. And by the way, when you're getting your driver's licenses, once you have your own car, first thing you do want to do, adjust your headrest, because often they're not at the right height. And that simple prevention, almost all of you statistically will be in one accident in your life. That simple little move can save you a lot of aches and pains. It's easy to do. It takes 15 seconds. Okay. So, head wants to remain at rest. The headrest applies, and I'll put in brackets, soft force on the head to keep it with the rest of your body. Now, if you didn't know this, you would think that your head had gone backwards, but in fact, the headrest accelerates your head forwards. This is why I've said to you, our bodies are backwards accelerometers. What our bodies really can detect is our own inertia, our resistance to force. We can feel it. It's always the opposite direction. I think I can get you started on some of the homework. Let me double check here. Yeah. So I think you can do part 1, number 1. So in all of these, she's at rest, which means the forces are, I'm looking for a word that begins with letter B, balance. So whatever the force down is, that has to equal the force up. And so she weighs 300 newtons. So what's the force down on her? 300 newtons. So what must the scale be experiencing or applying a force up at? What about in this situation here? Courtney, you're right. 150 each. What about situation C? 100 each, I think. Yes? 100 each for situation C. Right? What about situation D? Each one of them is going to feel 300 because we're not splitting the force between two ropes. So each one of them is going to read 300 newtons. What about situation F? Now, this picture is meant to show that she's barely putting any force on her hand, so she's basically still dangling in midair. And so that rope is still having to apply 300 newtons of force, otherwise she'd be falling. What about situation G? I don't care about all this garbage. Yep, 300. If it's one rope, it's taking all the force. How do I know it's 300? Because the question told me she's at rest, and that means the forces are, I'm looking for a word that begins with the letter B, which gives me a huge advantage. Okay? You can also do 2 and 3 and 4. Oop. You can do 5. And we'll pause there.